Hi folks, welcome to chapter 8. In this chapter, we are going to be looking at energy. In our previous chapters, we did look at physical and chemical changes. Most physical and chemical changes are accompanied by changes in energy and temperature. So, the study of energy and temperature changes is what is called thermodynamics. So, when we study energy changes in chemical reactions, that is, in chemical changes, that is called thermochemistry. So, we are going to be looking at energy, work, and heat in this first part of this lecture. So, we are going to define what energy is, and energy can be defined as the ability to do work. There are two forms of energy that we'll be looking at here. We'll look at potential energy, which is the energy that is stored, and the kinetic energy, which is energy of motion. So let's look at the types of energy changes. We are going to be seeing that energy can change either in the form of heat, which is the transfer of kinetic energy, or in the form of work, which is the transfer of energy from one form to another. Now we are going to use an analogy here to heat and work. So the first thing here is that you have wealth and spending. So I'm going to link wealth and spending to energy, heat, and work. So for example, you have money, you have wealth, which is in terms of dollars. So you can spend that money to buy something. For example, here you have this guy who has money. He's going to spend his money by buying a hot dog and a soda. So in the course of doing that, his wealth is transferred from him to this seller of the hot dogs and the soda. So when he spends the money, he gets the soda and the hot dogs. So that is spending. In spending, wealth is transferred from one person to another. Now, in energy, for energy to be transferred from one system or one substance to another, that is in form of heat and work. Just like as for money to be transferred, the wealth to be transferred from one person to the other is through spending. For energy to be transferred from one substance or one object to the other is through heat and work. Now we are going to look at the units of energy. There are so many units of energy. The SI unit for energy, or you can say is the IUPAC unit, is the joule, and 1 joule is equivalent to 1 kilogram meter square per second squared. Another unit of energy is the British thermal unit, and 1 British thermal unit is equivalent to 1055 joules. We also have the 1 kilowatt hour. We have the kilowatt hour, and 1 kilowatt hour is equivalent to 3.6 times 10 to the 6 joule. We also have the calorie with the lowercase c, which is equivalent to 4.184 joules, and we also have the calorie with the capital C, which is equivalent to 1 kilocal or 1000 calories. Based on the circumstance that we find ourselves, we use different units of energy. For example, if we are talking about space heaters, we are going to be talking about the British thermal unit. If we are talking about electrical energy, we are going to be talking about the kilowatt hour. And if we are talking about the nutritional value, we are going to be talking about the calories, which is the calorie with the uppercase C, which is the kilocal or 1000 calories. So let's look at the relationship between energy, heat, and work. For example, let's say you have a piston here and you have gasoline in this system. So the gasoline in the piston, when it's ignited, it burns, and the air in the piston pushes the piston up, and the piston starts the engine of the car, for example. So as the piston moves up, it does work. So it actually expands and does work. Some of that energy as well is being transferred as heat. So not all the energy is converted to that work. Some of it is lost to the surrounding as heat. So the sum of the work that is done by expanding the piston and the heat that is lost to the surrounding is the energy. So the sum of the work and the heat is energy. So we can represent it mathematically as delta E is equal to Q plus W. So the energy is the sum of the heat and the work. So what will happen now if we have a piston and it is sealed and it cannot move? So if the piston is sealed and we still burn the gasoline in this system, what will happen is that all of the energy will be converted to heat. And here, the work will be zero because the piston does not move. One thing you should know is that the energy is still going to be the same. Though there is no work, all of the energy will be converted to heat. So everything here in this system is heat. Now let's look at an example here. A small sample of propane burns, producing carbon dioxide and water vapor. As the hot gas mixture expands, it releases 20.0 kilojoules of heat and does 31.0 kilojoules of work pushing against a piston. What is the total amount of energy released in this reaction? So the first thing that we have to do, we are looking for the total amount of energy that is released. And we have said energy is the sum of the work and the heat. So the first thing we state our formula, the energy released is the sum of the heat and the work. Now in this question, it releases 20.0 kilojoules of heat and it does work, which is 31.0 kilojoules. So for us to calculate the total amount of energy, it is the sum of the heat and the work, which is 20.0 kilojoules plus 31.0 kilojoules. That gives us 51.0 kilojoules of the total amount of energy that is released. Now we are going to look at what is called endothermic and exothermic changes. Now we are going to get back into that system of the piston and we look at it in terms of what is happening in the system. Now we are going to look at it chemically. So we look at the propane, the gas, the gasoline that was found in that system, which is actually octane. So when it burns with the air in that system, it produces carbon dioxide, water, and great amount of heat. So when heat is released, this is called an exothermic change. Now, when the reverse occurs, when heat is absorbed in the system, this is known as an endothermic change. For example, for ice to melt, ice needs to absorb heat. So when ice absorbs heat, this is called an endothermic change. So exothermic change releases heat, while an endothermic change absorbs heat. So we could write out the equation for the endothermic process like energy. The ice needs to absorb energy to be converted to liquid water. Now, let's see how we can identify the system and the surroundings. When we were talking of this piston, we have only been talking of the piston and how the energy is released. So we are going to define a system and we are also going to define the surrounding. So what is a system in thermochemistry? The system is defined as the part of the universe that we are studying. So if we choose the piston here and this system, this is called the system. And for the surrounding is every other thing a part of the system. So the surrounding is the rest of the universe. Now, here is a question. Looking at this picture, you see an ice pack here being placed on an injured ankle. Now the question is heat being released or absorbed? Alright, for us to be able to answer this question, we must first of all define our system. If we don't define the system, we will be unable to answer that question. So if we define the system, we'll be able to answer the question. If our system is the ice pack, it means the ice pack is going to absorb heat. And if it absorbs heat, it means Q will be positive. And for the injured ankle, if the injured ankle is a system, it means that it is going to lose heat. And if it loses heat, Q will be negative. So for us to answer this question, we must define the system and the surrounding. Now, let's look at the direction of energy change. We've said the energy change can only take place in form of heat and work. That is called the first law of thermodynamics. So always remember that the first law is defined as for the energy to change, it can either change in form of heat or work. Now let's look at the direction of energy change in terms of the heat. So when the heat is released, that is an exothermic reaction or an exothermic change. When heat is released, Q is negative. And when heat is absorbed for an endothermic process, Q is positive. So when the system absorbs heat, Q is positive. When the system releases heat, Q is negative. Now, let's look at energy in terms of work. So what happens when the system does work on the surroundings? So when the system does work on the surroundings, it releases energy. And if it releases energy, W becomes negative. Now, if the surrounding does work on the system, it means that the system absorbs heat, it absorbs energy, and W is positive. So you have to be able to know when Q and W is positive or negative. For Q to be negative, it means that the system is losing heat. And for W to be negative, it means that the system is doing work to the surrounding. For Q to be positive, it means that the system absorbs heat. And for W to be positive, it means that the surrounding does work to the system. Now, we are going to look at what we call the law of conservation of energy. And the law of conservation of energy states that energy cannot be created or destroyed. We are going to look at another analogy here. Let's say you are playing a game, right? You have two players and you give them money. So player 1 and player 2 have money. The money can only move from player 1 to player 2 or from player 2 to player 1. So the money cannot get out of that playing system. That is the same like the energy. So for energy, the energy can only move between the system or the surrounding. You cannot lose any energy. So that brings us to state that the energy of the system is equal to the energy of the surrounding. So the energy cannot be lost. So you cannot create energy and you cannot destroy energy. Let's look at an example here. A chemical reaction releases 200 joules of heat energy to its surroundings. Write this change of energy for the system, which is the chemical reaction, and for the surroundings. Now, remember we said for heat, when the system does work, when the system loses heat, when it releases heat, Q is negative. And when it absorbs heat, Q is positive. So in this equation, in this question, we've been told that the chemical reaction, which is a system, releases 200 joules of heat to the surrounding. Now we have to write an equation in terms of the system and the surrounding. Now, for the system, we see that it releases heat, which means that delta E, which is energy, is going to be negative 200 because it loses heat. Now for the surrounding is gaining heat, and as it gains heat, it means that delta E is going to be positive. Alright, so that is how you demonstrate it for the system and for the surrounding. So let's look at a summary of what we've seen in this part of this lecture. We have said the energy change of a system can either occur in terms of heat or as work. And we've said the system is the part of the universe that we have chosen to study, and every other thing else is the surrounding. We also defined exothermic reaction that an exothermic reaction is a case where the system releases heat, and for an endothermic reaction, the system absorbs heat. We also said the energy is not created or destroyed in chemical reactions, and that is called the law of conservation of energy.